continue our curve fitting today. So just a quick review of why would I want to curve fit, or why do I need to go through that exercise. First point that I want to recap with you is that typically you have some data, okay, and you would like the data comes from, for instance, experiments, or it comes from, in petroleum engineering, from logging. Okay? And you would like to learn from the data. For instance, you would like to figure out how does permeability depend on porosity. You know very well that it's not a simple thing. Permeability depends on at least 6 things. Okay? Porosity is one of them, grain size is another. Then you never have a single grain size, you actually have a great range of grain sizes. So maybe in that relationship there is a minimum grain size, maximum grain size, middle grain size, median grain size, you name it. Okay. Then you have a fluid in question. We typically assume permeability doesn't depend on the fluid except that it does. So as a model, I typically take viscosity of the fluid and Darcy's law separate, and so forth. So you know that the world is complex, but you will nevertheless, you would like to sort of infer certain simple functional relationships between one parameter and the other, which is really just sort of a projection of some sort of a multi-dimensional functional relationship. So you have data, and then you have 2 options. You could try to draw a curve through every data point, which is called interpolation. We will by and large skip that. Okay. Or you actually have a cloud of data, so imagine that there is actually much more points here. Then drawing a line through all of them is simply not an option. Okay. Then you're looking at a trend. This is basically a trend or regression line, and we will learn how to fit these. So here are 2 examples. This is basically Van Genuchten model going through capillary pressure versus saturation during drainage. Okay. So one can actually go and try to interpolate this. But you could also just do a fit to that model, and this is actually a fit. This is not interpolation, and it's a very good one. So I'm actually very close to all of the points. Or I have a cloud of points. This is for a sandstone, permeability versus porosity. And I noticed that these 2 models are kind of different types of curves. So one key thing to remember is that you have to pick the curve you're fitting first. So you look at the data and you choose the type of the relationship you're going to try to fit. Okay? So these are not straight lines, they're not linear. Okay? So it's some nonlinear function, and you are in charge of picking that function. Just picking blindly is not going to work. Okay. So the first one, the simplest one that we'd like to do, is the straight line, which is a trend or often called linear regression. Okay. So assume I have a bunch of points. I want to fit the line. Line is described by 2 parameters. Right? And here I'm calling them A0 and A1. So basically y is equal to A0 plus A1x describes the line. I'm looking for A0 and A1 that fit this data well. So my measurements are essentially, I refer to them as xi, yi, so this is x1, y1, x2, y2, x3, y3, x4, y4, and so forth. Okay? And I'd like to sort of minimize the error at that point. Now, the way I'm looking at the error, okay, is I'm summing up the differences between what is my measurement and my model. So my model is basically defined by this linear relationship. So I take A0 plus A1xi, that's going to be my yi here, and I look at the difference between the 2. So for instance, here, this line, this would be my yi kappa, and this would be my yi. So this difference is quite big. Okay? And here at this particular point, it's relatively small. Okay. So this is the difference, and I just take square of it. So I'm just looking at the positive value of those differences and summing them up. And I'm really trying to minimize this. Okay. So there was discussion we went into why is that the best choice that I'm not going to repeat now. So basically, I'm taking the differences between the measurements and the model and taking square of it and summing them up. So this is so-called sum of square of residuals. So this is referred to as a residual, okay, the difference between the model and the measurement. Great. So now let's look at how do we minimize this, okay? This SR is xi, yi for I is equal to 1 to n. That's my data. I know those numbers. Those are just numbers. They're not variables, okay? So I know them. What I don't know, or what I'm looking for, is a0 and a1. Okay? And this is a function that is always positive, and I'm looking for its minimum. Hopefully 0, but never really 0, but close to it, right? So what I know about functions, right, is that for the minimum of a function, I know that I have to have a derivative equal to 0. So in this case, I have multiple variables, a0 and a1. So basically, partial derivatives with respect to a0 and a1 will be 0. And that's where we were in our worksheet that we're going to continue working on today. And if you don't have a copy, I'll go upstairs to get some in a moment. But let me just explain conceptually. So basically what we do for any other model when I'm minimizing squares of residuals is I'm going to just take partial derivatives of this SR, sum of squares of residuals, with respect to each parameter I'm looking for. So in this case, it's a0 and a1, and I'm going to set them to 0. So here, if I had that, okay, if I actually took the partial derivative of this, it would be actually minus 2 sum of this, and then to the 1, and then basically with respect to a0, okay? So that would be it, and that's actually, so you have extras? Oh, perfect, there we go. So when I take these partial derivatives, okay, these sums are here, but I shouldn't necessarily be scared of them. You will actually find a system that is linear. These are numbers, n sum of xi. They look scary, but I know them. I know all of the xi's. I can compute the sum, right? So this is actually a linear system in a0 and a1. Okay? I know how to solve linear systems. So solving for a0, a1 is solving this linear system. So what I'd like you to do, you basically solve the first part, where we actually took the case, a simple case where I have only 2 points. So my n is equal to 2, and this sum is really just x1 plus x2, and so forth. Okay? So I just want you to work that out on paper to just see the process, because this is basically the procedure that you would follow in any other case as well. So these sums, so basically take the sheet, and I'm actually projected 2, and let's go through the other 2 examples. And I posted PDF of the sheet as well as PDF of this this lecture on Canvas if you need it. So basically we worked through this last time. If you don't have it, we'll work through it quickly again. And now move to 3 and 4, set both partial derivatives to 0. And come up with the matrix form of the system in a0 and a1. And here, since this is a 2x2 systems, there is a suggestion, well, by the way, there is the simple Kramer's rule that will give you the solutions immediately. So I want you to come up with those solutions for the case of a 2x2 system. And while you're working on it, I'll be right back. Bless you. I'll be right back. How are we doing? Apparently we're not doing very well. Are you getting something similar to this? N is equal to 2? Maybe? Maybe. So what you should get in number 3 should be 2a0 plus, this is x1 plus x2 times a1 is equal to y1 plus y2 for 2 points, right? And then x1 plus x2 times a0 plus x1 squared plus x2 squared times a1 is equal to x1 y1 plus x2 y2. That's a double check for what you should get in number 2. Try to see it or get it. So the matrix version of that is then what? These are your unknowns. What do I have here? So for n is equal to 2, you have 2 here, right? x1 plus x2, x1 plus x2, and x1 squared plus x2 squared. And here you have y1 plus y2 and x1 y1 plus x2 y2. This one's about Did everybody get here? Should I wait for a couple of more minutes? You can work it out. Yes.
I'm getting 2 in front of them, so n a naught plus sum of xi.
Yeah, you're getting 2 because n is equal to 2 in your example.
Right, but 2 as well in front of them.
In front of this?
Yes. No, so if you, here you can actually divide by 2 because there's a 0. So then, but you would have a sum of a zeros, which is n of them. So if this one was just a sum, it would be, not going to be visible on the movie, but oh well. What I would get is minus 2 times y1 plus a0 plus a1 x1. Oh, excuse me, minus. Minus 2 y2 is equal to 0, correct? I can divide by minus 2. So this is just that. So what I will have is minus 2a0 minus a1 times x1 plus x2, okay, is equal to, when I put the other stuff on the other side, is this. Therefore, this is 2a0 plus x1 plus x2 a1 is equal to y1 plus y2 when I multiply by -1. And that's my first equation right there. Did you figure out where your mistake was? You think so? So again, there's a0 plus a0, but there's x1 plus x2. So there's no 2 in. Any other questions? And similar, I would get the other one. So if I have my data come in as a vector x and vector y, with elements xi, yi, is this difficult to find, to solve? So if I asked you to program linear regression, you would have xi and yi vectors of data as input, right? And you would just put together this system. So you would just really compute these sums and put the coefficients in a matrix and find it. Now this is a 2 by 2, so in number 4, because it's a 2 by 2, there's actually a ready-to-go solution to a 2 by 2 system. So just work it out and find it what it is, based on the little system that you came up with in part 3.
So here in the worksheet for the 2 points, this is a ready-to-go formula for solution for this system, so all you need to do is apply it to this one. Yes?
So this first equation I just derived right here. Yes? And the second one you would get from that partial derivative of SR with respect to A1. Okay?
So basically, here it's a little more general, but this is, if I did the derivative of this with respect to A1, okay, it would be 2 times sum of 2 times this, okay, and times minus xi, because that's what's sitting next to A1. Xi is just a number, okay, so it's not a variable in this case. So that's basically the sum of minus 2 times this times xi. So when you actually write this down for just having 2 points, you would get this equation here. And just divide it by minus 2. So it's a little bit of algebra, it's a little bit of writing.
But conceptually what I'm doing is I'm taking partial derivatives of this sum with respect to A1 and A0, because I know that that has to be true for a minimum of that function. And since function is positive, it's likely to have minimum, it's
Maximum, good luck looking for. So again, if I had vectors xi and yi to work with, and we're going to go through the example, I just want to go through this part first. Or actually, do you want to program immediately or program after I teach about something else at the very end? Want to program immediately?
Yeah.
May as well? All right. Well, let's... The data will be... Data is given here. Okay?
And for this part 1 programming, I want you to create linear regression.m that takes this data and just do.
So I'm going to actually create a what? So I'm going to write the separate exercise. So here's the data. Create linear regression dot m function that takes x, y vectors as input and provides linear fit parameters A0, A1 as output. And formulas essentially you have worked out on your sheet, or you can, how you really choose, so you can write down what the solution is to this system. This is just for your exercise for a 2x2. I'm gonna start easy, so essentially so this is how function should look like, right? It should have vectors x and y as input, and it should give back A0, A1. So part 4 should give you actually this here, A0 and A1 in terms of just having two of these, x1 plus x2, right? And x1, y1 plus x2, y2, because we had only, on our worksheet, we had only 2 points. But this is more general sum if I have more data. And we're here to help. Programming. So if you actually plug in your in this Kramer's rule, you will get these formulas. This is just their stated more general form. If you need to program just to have them right there, so you don't have to.
So what function do you use that?
Yes, because you want function to work in general case, not just for 2 points. So 2 points is just to work it out in the paper so you understand the process. If you plug in, yeah, if you plug in, so here you have another linear system. If you plug in, instead of A0, A1, this is your A0, this is your A1.
plug in these values. Yeah. But then when you generalize that endpoints, you get those two formulas that are sitting there. Because in general, some overall that's square. Just to see. So work. Okay, so in the first go, use sum function. Use it. Use sum function. You can use sum function to get these sums. As long as you know what would you do if you didn't have some function. I'll just do it. You all have the printout, so I'll just do this. So when I say you can use sum function, then one of these sums, let's call it sum x, is sum of x. And if sum function is not available, okay, then you would do, so n is number of elements of x. Then you would do sum x is equal to 0 for I is 1 through n. Sum x is x of I plus sum x, end. So I'm just saying this is what you would do if you didn't have sum function. But I say you can use it. So use it. So that's vectorization is available. And MATLAB niceties are available. 2 exams by now, I would assume that you know how to do this if you have time to sit down. Sum of y's is easy. Sum of x's is easy. How do I get this quickly? In a 1 line of code. Sum of dot, right? Dot times what? Does everybody see that? So a vector that has element by element, x of I times yi is x dot times y, right? That's a vector. So if I sum that, I'm going to get this sum. This is when vectorization is available. Otherwise, I don't do it by studying.
How do you do the sum of xi, all of it squared, using for loop?
Well, you would compute this sum and then it's squared, sum x times sum x. That's sum x times sum x.
Oh, curious. Like,
But if you don't have vectorization available, then you have to go through something like this, which is why we did that practice with those loops and sums. And in most programming languages, you have to do that. You can't do this. Do we see this one?
Or this is the same?
Do I have everything I need? All of the sums? Maybe. Maybe not.
We want sum y2 as well.
I don't need, you mean y squared?
Y squared.
No, I don't seem to need it. Do you see it anywhere? No, so no.
Sum of squares, xi, yi, xi squared, but I don't see sum of yi squared.
So then this is some x times some xy minus some x squares times some y divided by some x squared minus n times some x.
Do you agree?
Check on me, I'm doing this on the fly. Therefore, I'm going to have typos. But most importantly, check on yourself. And yes, I will expect you to submit this online, so. So I typed this into a script to run. How do I check that it's good?
I computed some numbers, are they any good? Am I close? Did I have a typo? Well, let's plot the data first.
Okay. Whoops. I actually want it as, I don't know, circles. There we go. That's my data. Now, what would be my model? How do I plot my model, my linear model?
Just give me 1 minute. If I have data and I computed my A0 and A1, what is my model, my linear model for this? It's a line A0 plus A1 times X, right?
So I can plot that. X and A0. And now I will actually then see whether I had a typo or not. I don't know.
So this is my model. That's what I actually computed as a model from this data, right?
And I'm just put that as a red line. And apparently I did have a typo because it's not even on the same scale. So I have to go and debug because it doesn't even, oh, I didn't do, hold on. Maybe not, maybe I'm still good. Oh no, I'm good, no typos.
What were your parameters again?
A0 and A1, that's what I got from my linear regression.
Let me quickly see what they are. A0 and A1. But this is how you check, okay? Do you get the point how I'm plotting things?
Yeah, but
So I plotted the points, okay? And I plotted the line. And line is simply A0 plus A1 times X, X being the data that comes. So please sign the papers and give them to us. They're going to be quiz points. And we will work with this file a little more. I'll ask you to submit it on Monday. Mm-hmm. That's fine. Hmm? That's fine. Whatever you did on the, I'm going to collect code on Monday. So code you can hold on to. Right now, just sign the papers so that way I know you were here and you were working on it. All right.